Thank you for the introduction. So my name is Alain Portavoce. I'm working at the Institute of Materials, Microelectronics and Nanosciences of Provence in Marseille. And today I will talk about interface carrier filtering effect on the Seebeck coefficient of a bilayer made of a Mn5Ge3 film and a germanium film. So this is the outline of my talk. As an introduction, I will recall some basics about thermoelectric materials engineering using interfaces. I will say a few words about interfaces in multi-phase thermoelectric materials before to present our results about the contribution of this interface between Mn5Ge3 and germanium to carrier transport and to carrier filtering. And finally, I will conclude. So thermoelectricity conversion efficiency depend on the temperature gradient, but also on this coefficient, Zt, which is actually the figure of merit of thermoelectric materials. And this figure of merit is exclusively depending on intrinsic properties of the materials through the Seebeck coefficient S, the electrical conductivity sigma, or the thermal conductivity through electron or the lattice. So on this graphic, I present the power generation efficiency of different technology with some conversion equivalents in Zt, and we see that in order to produce competitive thermoelectric devices, we need to obtain Zt close to 3 or higher. So we are always in the search of more efficient materials, and a large panel of materials were investigated, such as semiconductors, chalcogenide, Hustler, etc. So as you can see on this graphic, where you can follow the variation of Zt of different materials versus temperature. And we can note that for application close to room temperature, around 300 Kelvin, the most efficient materials are actually materials made of toxic or rare elements. So another way would be also to try to engineer the materials we already know, and this, for example, using the effects of interfaces. So as an example, I present here for the same materials, a polycrystalline layer, how the lattice thermal conductivity is varying versus the grain size in the polycrystals. And we see that when the grain size decreases, which means that the number of interfaces is increasing, we observe a decrease of the lattice thermal conductivity, and this decrease of lattice thermal conductivity leads to an increase of Zt. An increase of Zt should be also obtained through the Seebeck coefficient, as the Seebeck coefficient is proportional to the average energy of the charge carriers by unit of charge per Kelvin. And you can see in this equation, for metals or degenerated semiconductors, the Seebeck coefficient depends on the electronic band structure through the effective mass of the carriers. It depends on the charge carrier concentration and also on the carrier scattering. So the idea is that if we can increase the average energy of the charge carriers, we can increase the Seebeck coefficient, and then we will increase Zt. And this can be done if we have an energy barrier for the charge carriers inside the materials, as it is pictured on this schematic. If we have a barrier that can forbid low energy carriers to pass, then we will increase the average energy of the carriers, and we will decrease their number, which will lead to an increase of the Seebeck coefficient, and we will have an energy filtering effect. So not all the interfaces, but some interfaces are expected to promote energy filtering, especially in multi-phase thermoelectric materials. And we can consider first two types of interfaces. Some interfaces that correspond to a Schottky contact, especially between a metal and a semiconductor. And in this case, we have actually an energy barrier at the interface between the metal and the semiconductor, or interfaces that correspond to ohmic contact, where we do not have a barrier energy between the metal and the semiconductor, and the IV curve follow a linear law, which means that the current increases linearly with the voltage. So let's consider our case for the interface between Mn5Ge3 and germanium. So on this graphic, I present the variation of the electrical conductivity for a single film of Mn5Ge3 and a single film of germanium. We see that for Mn5Ge3, the electrical conductivity decreases when the temperature increases, which is the behavior of a metal, while for the germanium film, the electrical conductivity increases with the temperature, which corresponds to the behavior of a semiconductor. We also measure the AV curve for this contact between Mn5Ge3 and germanium, and we see that the current follow a linear law versus the voltage, which means that this interface corresponds to an ohmic contact. So we will also consider two different geometry, the parallel phase geometry. So in this case, the temperature gradient is parallel to the interface, so the carrier are moving parallelly along the gradient of temperature, and the carriers are moving in the direction parallel to the interface toward the cold side. And the effective Seebeck coefficient can be written this way if the interface has no effect, which means that if the interface does not play the role of a channel to transport the carriers. The second geometry is the serial phase geometry. So in this case, germanium and Mn5Ge3 are placed in series in the temperature gradient, and which means that the charge carriers move perpendicularly to the interface. Okay, so in this case, the effective Seebeck coefficient should be written as the sum of the two Seebeck coefficients in the 5,3 compound and germanium weighted by the volume fraction of each phase that cross the carriers. Also, we can note that if we place the germanium in the hot side and measure a Seebeck, the S1, and if we place the germanium in the cold side and measure another effective Seebeck coefficient, these two coefficients should be the same if we have no effect of the interface. So I present here the geometry we use for our experimental measurements. For the parallel geometry, we use this classical geometry. We have the bilayer, and we measure the voltage along the temperature gradient. And in the case of the serial geometry, we measured the voltage through a step between Mn5Ge3 film and the germanium film. So Mn5Ge3 and germanium thin films were deposited on glass substrate by magnetron sputtering, and we investigated temperature close to 300 Kelvin for room temperature applications. So let's investigate what is the interface between Mn5Ge3 and germanium on carrier transport. So on this graphic, I present the variation of the Seebeck coefficient versus temperature for a single film on germanium in red, for a single film of Mn5Ge3 here in purple. We see that the Seebeck coefficient of germanium is positive, which means that our semiconductor is p-type, and the majority carriers are holes, while the Seebeck coefficient of the Mn5Ge3 layer is negative, which means the layer is n-type, and the majority carriers are electrons. In blue here, you have the measurements that were performed on the bilayer, and in black, you have the value of the effective Seebeck coefficient calculated according to this equation. And we see that we have a pretty good agreement, which means that the interface does not play the role of a channel for charge carriers, and has no effect on the Seebeck coefficient. So now let's investigate the contribution of this interface to carrier filter. So on this schematic, I remind you of the geometry we use for our measurements. And on this graphic, I present the variation of the Seebeck coefficient versus temperature. In the case where the germanium were placed in the cold side, which means that in this schematic, the gradient temperature is in this direction. And here in orange, the case of germanium placed in the hot side, which means that in this case the temperature gradient is in this direction. In red here you have the Seebeck coefficient of the germanium layer. In purple here you have the Seebeck coefficient of the Mn5Ge3 layer, and in black here you have the Seebeck coefficient of the bilayer. We can see that the Seebeck measurements through the step here is different from the single films, either germanium and Mn5Ge3. It's different from the measured the Seebeck measured on the bilayer, and it cannot be reproduced using the equation of the serial phase geometry, which is here. And we can note that this effective Seebeck coefficient is different when charge carriers cross the interface from germanium to Mn5Ge3, which means that when germanium is in the hot side, it gives this Seebeck, and from the case where the carriers cross the interface from Mn5Ge3 to germanium, when germanium is in the cold side, which corresponds to these measurements. So we have here a clear impact of the interface on the Seebeck coefficient. So we measure several times the Seebeck coefficient on the same sample in order to check the reproducibility of the measurement. So on this graphic I present the variation of the Seebeck coefficient versus temperature, measured on the same sample 4 times, 2 times with the germanium placed in the cold side of the temperature gradients, and 2 times where the germanium were placed in the hot side of the temperature gradient. So we can see that the measurements are reproducible. We observe some differences here with the arrows, that is highlighted by the arrows, which displayed a stochastic character. And we can see that the effective Seebeck coefficient exhibits higher value if the carrier moves from hot Mn5Ge3 to cold germanium, as you can see here. And this Seebeck coefficient shows opposite variation versus temperature, depending on the carrier direction through the interface. But we observe a kind of symmetrical behavior around 30 microvolts per Kelvin for this sample, which is around here. So in order to understand that, once we have to go back to the expression of this Seebeck coefficient, effective Seebeck coefficient, that should be the sum of the 2 Seebeck coefficients for the 5,3 compound and germanium, weighted by a coefficient here. But we have to understand that in germanium, as it is a doped layer, p-type, actually we have 2 channels because we have 2 carriers. The holes, the majority carriers, and the electron, the minority carriers, that correspond to the bipolar effect of the semiconductor. Also, if we just consider that the Seebeck coefficient is proportional to the concentration of the carrier at the power minus 2/3 for the holes and the electron, and also that the conductivity of holes or electron are proportional to the concentration of holes or electron, then the Seebeck coefficient, and also considering that this part here is almost constant, then the Seebeck coefficient, the effective Seebeck coefficient, is proportional to the germanium Seebeck coefficient, which is proportional to this fraction. And on this graphic, I plot this fraction, considering in blue that the concentration of holes is constant and we increase the concentration of electron, and we have this type of shape. And in orange, when we consider that the concentration of electron is constant and we increase the concentration of holes, and we have here. So we see here a kind of symmetrical effect as we saw on the experiments, and this would mean that the opposite variation of the Seebeck coefficient that we observe with opposite carrier diffusion direction can be interpreted as mostly resulting from the modification of the charge carrier concentration in germanium versus temperature due to the interface. So this would mean that the ratio between the electron concentration and the hole concentration seems to increase versus temperature if carriers cross the interface from Mn5Ge3 to germanium, while this ratio seems to decrease versus temperature if carriers cross the interface from germanium to Mn5Ge3. So in order to to investigate this possibility, we perform additional measurements in a different geometry. In this time, the temperature gradient is in this direction, and we measure the diffusion coefficient either here on the two layers, and we can imagine that this Seebeck coefficient should be close to the Seebeck coefficient of the bilayer, and we measure the Seebeck coefficient here on the down terrace where there is germanium, and we expect this Seebeck coefficient to be the same as germanium. So I present on this graphic the variation of the Seebeck coefficient versus temperature. In red here, this is the Seebeck coefficient measured on the down terrace on germanium, and we see that this coefficient is quite lower than the case of the single film of germanium. The blue measurements here correspond to the Seebeck coefficient measured here on the two layers, and in black here, this is the Seebeck coefficient measured on the film, on the bilayer, sorry. And we see that on this upper terrace, the Seebeck coefficient is a little higher than the Seebeck coefficient measured in this geometry on the bilayer, and even one part start to be positive, change sign. So what we have also performed is, after these measurements, we removed completely the layer Mn5Ge3 and again measure the germanium Seebeck coefficient, and this time from this value with the film we go to this value without the film. So the Seebeck coefficient in germanium increases. So this shows that the interface, as expected, has a strong effect on bipolar germanium. So in conclusion, we investigated the influence of the interface between an N-type Mn5Ge3 films and a P-type germanium film experimentally. We showed that the Mn5Ge3 germanium interface does not contribute to charge carrier transport, but this interface is ohmic and contributes to charge carrier filtering. Filtering results from carrier injection or recombination at the interface, which depends on the direction of the carrier flux. The charge carrier concentration in the metal being significantly higher than in the semiconductor, interfacial carrier injection or recombination have a stronger effect in the semiconductor. Thank you for your attention.